Thank you for joining. My name is Andre Richter, and today I will talk about bridging the gap between electronic and photonic design. At first, I will talk about the hierarchy of electronic and photonic simulations. Afterwards, I will discuss two application cases. The first one on the transceiver design using a microring modulator built in silicon photonics, and afterwards on the wideband transmission over multimode fiber using multimode VCSELs. At the end, I will summarize my presentation. Regarding the design flow of electro-optical interconnect solutions. Here we see an example on the left-hand side for the 200G base FR4 transceiver. On the right-hand side, we depict here printed circuit board realization. Typically, what these type of transceivers have in common is that the optical and electrical parts are very tied together. So what we need a very good co-design on the electronic design, so of the EDA tools, and of the photonic design environment, so the PDA tools. So in the electronic design, you account for the ASICs, PCBs, interconnect, etc. And on the optical design, you account for the accurate modeling of optical components and technologies, such as the light wave generation and detection, but also the multiplexers, demultiplexers, and fiber transmission. Considering the simulation hierarchy, there are two different levels which you can account for. At the bottom part, we see here detailed modeling approaches, where we would have on the optical domain, for instance, our photonic simulator provided by VPI, allowing you a detailed analysis of lasers, modulators, amplifiers, etc. And on the electrical circuit simulations, using SPICE type of simulator, performing, for instance, modified nodal analysis to account for the aspects of drivers, transimpedance amplifiers, etc. On the top level simulation, you could use, for instance, the channel simulation domain by IDS, which allows you to use fast behavioral AMI models and S parameters to describe functions such as the DSP, DAC, ADCs, and ASICs. What we've showed more recently is a tight integration of Keysight's channel simulation and our photonic simulator, allowing you a top-level EOE simulation. If you're interested in, dive into the YouTube video, which is depicted here. Further, what I will show you today is the integration of a SPICE simulator into our domain, allowing you the integration of all three simulation domains. Okay, here's the first application case. Microring modulators are very promising when it comes to a tight integration of electronics and optics. Because of their small size, they're good candidates for overcoming the integration trade-offs of commodity-based Mach-10 modulators. We see on the right-hand side, the top here, the photonic integrated circuit model with a laser and the microring modulators. And here we see the electric integrated circuits with the drivers and serializers. So if you want to simulate the whole structures, then an EOE simulation domain would be needed, including the detailed modeling of the electrical parts. So let's start with the top-level design, and here's a typical design flow in channel simulation realized in ADS. We start here with the electrical function of the transmitter, the redriver, and the receiver modules, representing the ASICs or FPGA chips, and also performing functions like equalization, gain adjustment, etc. They are connected via transmission lines or vias, so PCB data, which can be included in this domain via measured data, so S parameters, or direct circuit models. In between these electrical transmitter and receiver parts, we have the optical link. And in this case, we simulate this optical link using our photonic simulation VPI environment. We will read in on the left-hand side data from ADS, and at the end, give it back to the ADS environment. Here on the TOSA and ROSA side, we have simplified or behavioral models for the nonlinear microring modulator driver and for the transimpedance amplifier at the receiver side. And we perform detailed modeling of the optical and electrical characterizations of this microring modulator and the fiber transmission part. So in the following, I will focus on this MRM here. To simulate in detail the physical characteristics of an MRM, you could build the structure up using a detailed photonic integrated circuit environment as depicted here. So we have a light coming in, we have our ring structure here with some phase section and our junction model, which is then driven or controlled by our electrical input voltages. However, for system application, it is desirable to have a discrete system model which then directly solve the propagation equations over this circuit here. And here we see on the right-hand side a few of these characteristics measured by applying different voltages and investigating its characteristics with respect to frequency and wavelengths. So on the right-hand side, for instance, we can see clearly that there's a nonlinear response being static and dynamic characteristics of the MM requiring very detailed or accurate predistortion of the optical domain. So this is all on the optical modeling then, but it's also important to model appropriately the equivalent electrical circuit of this microring modulator. And this is how the modulator would be seen from the electrical circuits driving this modulator itself. It's not replacing the modulator optical characteristics, but it's actually how the modulator affects the electrical circuits before that. And for this, you could use a so-called equivalent electrical circuit model for this modulator. And the typical ways of doing this, either linearizing this using an S-matrix approach or using a nonlinear modeling via SPICE cosimulation then. We could have here this representation of a microring modulator and its equivalent electrical circuit and build this all up into our linearized S-matrix model, so wire bonding and the intrinsic MM circuits. And then perform simulations of the transfer function, for instance, for two different input voltages. The green one would be 5 volt, the blue one would be 0 volt. And with respect to this junction capacitance, would have a differently fixed value for each of them. However, in real life, this junction capacitance has a strong dependence on reverse voltage. So using a SPICE model, you can account for this nonlinearity by approximating this curve by a piecewise linear function. And then if you use the SPICE implementation of this equivalent circuit, then you would see actually its transfer characteristics here for these given input scenarios. So as the junction capacitance is strongly dependent on the voltage and the equivalent electrical circuit is nonlinear, and this requires you to use a SPICE. However, for small signal modeling, a linear approximation using S-matrix domain is also possible. So at the output, after the simulations, we see on the left-hand side the outputs when we linearize the equivalent circuit using S-matrix domain modeling. On the right-hand side, the nonlinear modeling of this equivalent circuit using a SPICE co-simulation. On the top, we have typical output eye diagrams of the optical link and the detection and transimpedance amplifier. We see, for instance, here the different levels of the PAM4 intersimple interferences here. And then these plots would be after the differential receiver and equalization at the receiver side in ABS. And then we can investigate the overall bit error rate and make adjustments on the optimization of the parameters. So what I've shown so far is actually the microring modulator, but we also have here drivers and TIEs. And in a very much a similar way as we do this for the equivalent circuit for the microring modulator, we can also integrate complex SPICE simulations for the drivers, as shown here on the left-hand side. For instance, this one would account for pre-distorting the electrical circuit to overcome these nonlinearities of the microring modulators. And on the right-hand side, we see an example for a wideband transimpedance amplifier, giving you something like 40 gigahertz 3 dB bandwidth. So they can also be integrated in a similar way as I've shown you before. Okay, for the second example, I want to demonstrate you how you can do a wideband transmission using multimode fiber propagation. Again, similarly, we send in here our data from the AES environment, our case providing us 26 gigabaud signals, two wavelengths. These wavelengths are generated by 2 VCSELs, which are then coupled into the multimode fiber, and then after detection being sent back to the ADS environment. Transmission is performed over 150 meters multimode fiber. So again, for the VCSEL driver and for the transimpedance amplifier, we use simplified behavioral models. Here we have the VCSEL model, which requires a detailed modeling of the electrical and optical characteristics. Here we have the multimode fiber, which allows you to account for the wavelength dependence characteristics of the differential group delay, of chromatic dispersion, and nonlinear effects. Very important for this type of systems is actually that you are able to accurately account for the VCSEL fiber coupling, including like free space propagation over some lens system into the fiber then, and considering offset conditions, etc. And as this is very specific to the VCSEL and to this specific environment, it's very important to also perform characterization of these launch conditions, such as the standardized and circuit flux characterization depicted here. So let me now come to this VCSEL model in a bit more detail. For the VCSEL, as it is a very complex model, it has an electrical model and an optical model. The electrical model would emulate the characteristics of the VCSEL as it is seen from the driver driving the VCSEL, and the optical model would then actually take the input from the electrical part, so basically the driving current here, and then relate this to the photon and carrier dynamics in the laser. And as we do this here, we can implement this all into a single building block by first describing these equivalent circuit here by its proper equations, and then getting from this the driving current, and this current then would then relate directly to the photon and carrier dynamics. However, these equivalent circuits are dependent and specific for the different VCSELs from different vendors. So it's maybe more appropriate to separate the electrical modeling and the optical modeling of the VCSEL, and this can be done by, again, using a SPICE simulation engine. And here we have like two realization of equivalent circuits. They can be described by their corresponding netlists, and again, we can do the same characteristics as before, getting us a current, and then driving the optical model with this. Okay, in an overall scenario, then you would then start again from ADS to perform the top-level EOE channel simulation, and then from within start the optical link simulations in the VPI environment, accounting for the multimode VCSEL fiber characterization, and also includes SPICE interfaces to nonlinear electronics where needed. Typical output characteristics are seen here. So this would be, for instance, I diagram before we launch into the optical link. Here we see the spectrum of the two VCSEL models at 1850 and at 910 nanometers. See clearly the multimode characteristics here. So this is before it goes into the fiber. Here we see calculated coupling coefficients from the VCSEL into the fiber. And after fiber intersection, we see here a typical I diagram of the transimpedance amplifier before it goes back into ADS, where we perform equalization and can then have a look at the final bit error rate. So in summary, I presented you a design and simulation environment which accounts for the top-level co-design of the complete AOE interconnect solutions and of the co-simulation of integrated electronic and optical parts. This is enabled by the dynamic communication and seamless data transfer between individual design tools. And this allows you to account for quick behavioral models of complex electrical circuits, and doing this together with detailed optical and electro-optical models. If you want to integrate purely electrical components into the modeling environment, you can do this easily then by an integrated SPICE engine. Thank you very much for your attention. If you have questions, please visit us at vpphotonics.com. Stay tuned for more videos to come. Thank you.